we'll do one more of these, but I'll just do the talking. Every class, actually. Okay, so all right, let's say heights of men. What percentage of men are between 68 inches and 72 inches? So 5, 8, and 6 even. If the height of men is normally distributed with mean 70 inches and standard deviation 3 inches. Okay, so to do this, if we were to draw our picture, it looks like this. Mean of 70, I'm going to go out to 72 inches and down to 68 inches. And I want to know how much is in between there and there. Okay. So I have a pair of z-scores to figure out. I'm going to look up 72 minus 70 over 3, and I get a z-score of 0.6666. And do the same on the negative side, or on the lower side, which is 68. Okay. Because of my poor choice of numbers, they end up being negatives of each other. But this doesn't always have to be. Okay. How do I get the area in this middle here? Okay. Well, I would say that this middle piece can be found by taking the area to the left of z equal to positive 0.66, or 0.67 if I round, and then subtracting off the area to the left of negative 0.67. If I say this minus this, then what I will be left with is the part in the middle. So that's all I'm going to do. So I look up z equals positive 0.67, and I find that this piece area to the left of it is 0.7486. And I look up negative 0.67. And I get the area in this piece is 0.2514. So if I take the difference between those two, I will get what's in the middle. What is that? 4972. So just about 50%. Okay, so that's almost like the middle 50%. It's practically the IQ bar. Okay, is that good with everyone? All right, so I'm going to jump ahead. So this is all in chapter 4 in that one section on the normal distribution. You have a few exercises in your homework. There is a section on assessing normality. And I'll go over that when we use the computer. And I'm going to jump ahead to the end of chapter 5. going to use the normal Chapter 5, we're going to use the normal distribution to approximate the binomial distribution. So this is how it's going to work. The binomial distribution is discrete. It can only have whole number outcomes. Normal distribution is continuous. But when the binomial distribution has a large n, it looks like the normal distribution, okay? Now, different textbooks say different things. I think our textbook says 5, other textbooks say 10, okay? So if n times p is greater than or equal to, some say 5 or 10, okay? Depending on who you ask. Then the normal distribution can approximate the binomial. So if we flip a coin 30 times, probability that the coin lands heads is 0.5, n times p in that case is 15, and whether you ask the 5 or the 10 guy, they'll say yes, you can use the normal model to approximate. Okay. So let's say we flip a coin 30 times, okay? Probability probability of heads is equal to 0.5. And let's say I ask the question, what is the probability I get 23 or more heads? If we wanted to do this using the binomial distribution, what would I have to do? I would have to do 23 or more means y is equal to 23, or y is equal to 24, or y equals 25, or 26, all the way up to y equals 30, right? So y equals 23, 24, 25, all the way up to 30. So that's a lot of outcomes that I have to compute. And for every single one, I would have to do 30, choose 23, 0.5 to the 23, and 1 minus 0.5, which conveniently is also 0.5, to the 7, okay? Plus 30, choose 24, 0.5 to the 24, 0.5 to the 6, okay? Plus all the way up to 30, choose 30, 0.5 to the 30, 0.5 to the 0. Is that okay, this expansion?
So that we can find the auto integrity?
Yeah, we have to do that, and that's a pain in the butt. We don't want to do it. Okay? Can we agree we don't want to do this?
Yeah.
Okay. So this is what we would, if we want to use the binomial distribution, this is what we would have to do, but we don't want to do this. Okay. But that's how we would get the answer. Well, we can approximate it with the normal distribution, because if you look at the binomial distribution, it's discrete, but when NP is greater than 5 or 10 or whatever, okay, it looks like this. Something like this, okay? And this is a terrible illustration, but it looks like the normal distribution. Yes?
What is the p in this? Because 30 times 0.5, why would that be? Is that greater than 5 or 10?
Yeah, so 30 times 0.5
Oh, I'm sorry. I'm thinking 0.5 to the 30.
is equal to 15, okay? And that's greater than 10 or 5. Okay? I think our textbook says 5, and then another textbook I use says 10, and I can never remember which one is which. So. But it doesn't matter. 5 or 10. 10 to be on the safe side, 5 if you're feeling dangerous. Okay. Or adventurous, I should say. Well, it depends how good does your approximation need to be, right? If it needs to be really good, then it needs 10. Okay. If a bit of error is okay, 5 is probably good enough. So we're going to approximate the binomial distribution with the normal distribution, okay? Normal distribution needs a mean and a standard deviation. Binomial distribution takes an n and a p, okay? So how do we go from the n and the p to the mean and the standard deviation? Do you guys remember? So we need a mean and we need a standard deviation.
N times p.
Yeah, the mean is going to be n times p, and the standard deviation of the binomial is square root of n times p times 1 minus p. Okay. So the mean that we would use is 30 times 0.5. I would use a mean of 15. Okay. And the standard deviation would be the square root of 30 times 0.5 times 0.5. And that's 7 point. Square root of 7.5. I don't know what that is. 2 point something something something. Back in the day, you had to find square roots by hand, and that was very tedious. I don't think I know how to do that actually. Does anyone? Okay, so that's my standard deviation. Oh, this is going to be a terrible example. Because I realized 23 is just ridiculously high. Alright, okay. So what I want to do is I want to go figure out 23 okay? Now, imagine that we've got some normal distribution and it looks like this, okay? And we're trying to catch what 20. So I have a bar centered at 23. Technically, it is right there. So I have a bar centered at 23. 24 and 25, even at 22, and like that. Okay. And I want to know what's the probability of getting 23 or more. Okay. This is discrete. So do I include 23? And my answer, yes, I do. Okay. So I want to shade all of this bar 23. I want to shade bar for 24, bar for 25, 26, just like that. If I were to draw a line at 23, I would be missing half of my bar. So where should I draw my line? A little bit to the left. And where would you say that bar, where would I cut off? Because I've got another bar here centered at 22. So I would draw a cutoff line at 22.5. Can we see that? Because I want to include the bar for 23. So I'm drawing a cutoff at 22.5. So at this point, it becomes a normal model problem. It's y comes from a normal model with mean 15 and standard deviation 2.739. And now I'm drawing my cutoff at 22.5. So I have z is equal to 22.5 minus the mean of 15 divided by 2.739. And I think this is just going to be 2.74. I get a z score of 2.74, and I want to know what's the probability of getting that or more. So I look to the right. So how much do I have? 0, 0, 3, 1. So replacing this with a normal model, 22.5, and I want to get this area over here. I get 0.0031. So if I did all of this, my normal approximation says I would get an answer that's close to 0.0031. So that's looking up z is equal to 2.74 and finding the area to the right. Is that okay? This is where things change up, okay? So here I ask the question, what is the probability I get 23 or more heads? So in that case, I want to include 23 as part of my answer. If I change this just slightly, just change the words around to say, what is the probability I get more than 23 heads? What happens now?
You have to work with 23.5?
Yeah, so in this case, I don't want to include 23. I start at 24 and I go up. So if I ask, what is the probability that I get more than 23 heads? When I do my normal approximation, I don't want the bar for 23. I only want to get the bars starting at 24. So I would draw my cutoff at 23.5. Can you see that? Okay, so whether we go to 22.5 or 23.5 all depends on the wording of the question. And it's whether or not you want to include that particular answer. So there's this is called the continuity correction. Okay? Because we have a discrete distribution, the binomial, and we're approximating it with something continuous, the normal. And so there's a continuity correction of plus 0.5 or minus 0.5 going on in here. Okay, I hope that's okay. So, I'm going to bring down the screen here. Let me pause the video.
I accidentally bumped it a little bit.
You bumped it?
Yeah, it looks like it's still centered.
Is
It's
it
more
still
or less.